Okay, so this is actually not chapter 17, it's now chapter 19. It's called acid and base reactions. So it's going to be all about acid and base reactions. So first, let's establish what an acid and a base are. You already have an intuitive experience of this. You know, for example, that lemons taste sour or tart. That's because lemons have a high amount of acid in them, in particular citric acid for lemon juice. Also, if you take a substance that we call litmus paper and you touch it to a lemon or into some vinegar or anything like that, anything that's tart tasting, it'll turn the paper from blue to red. So litmus paper is actually made from a litmus tree, just a wood, and it turns out it changes color whenever it touches an acid or a base. If you touch litmus paper to a base, it goes the exact opposite way. It goes from blue to red. Acids have certain particular characteristic reactions, and we've seen these before. One of them is that they'll react with metals. So we did an experiment where we took magnesium and we added hydrochloric acid. And this was in 111. And it's going to produce hydrogen gas and magnesium chloride. So that reaction is familiar to us. Another one is whenever an acid reacts with what we call hydroxide bases. So that's basically an acid and a base reacting together. Whenever that happens, an acid and a base react together, it's going to produce water and some kind of salt. Sometimes NaCl and sometimes other salts, other ionic compounds. So when I say salt, what I mean is ionic substance. Finally, if it reacts with carbonates, it'll produce carbon dioxide. So carbonates are molecules that contain CO3 2-. That is one of the polyatomic groups on the back of your periodic table, and so we call that a carbonate. If some acid reacts with a carbonate, it's always going to produce carbon dioxide gas. So that's something that we'll be looking at as well. Acids and bases are often measured on the pH scale, which begins at 0 and goes all the way to 14. So for the purposes of our class, the pH scale is going to be from 0 to 14. Things that are lower in the scale are more acidic, and things that are higher up are what we call basic. Neutral means that it's a pH of 7 exactly, so right in the middle. Human blood is a little bit basic. It's a pH around 7.4 to 7.5. Baking soda is a little more basic than that, and soap. Cleaning agents in general tend to be alkaline. They tend to be basic. So, like your laundry soap has a pH somewhere around 10. That's why you should keep laundry soap away from little kids. It's not good for them to eat it. Bleach is really, really high in pH, 12.5. Ammonia is even higher than that. Yeah, so lots of familiar products are acids and bases. So first, we want to have a way of defining what an acid and a base means. Arrhenius was the first person to come up with a definition, and he thought that acids should be defined as something that when you put it in water, it makes excess H+ ions. Bases make hydroxide ions. So we're going to call the OH- hydroxide. That's another polyatomic on the back of your table. So hydroxide ions form when you have a base. So this second example is a base. The first example is an acid because it's producing H+. The next definition to come along was by Bronsted and Lowry. Two different scientists worked on this one. And basically, the difference between the Arrhenius definition and Bronsted-Lowry is that we have a lot more evidence that Bronsted-Lowry is actually physically true. The Arrhenius definition, where it produces H+, it works for simple systems, but The fact of the matter is we have never actually observed H plus existing by itself. Instead, what happens is when you have an acid like HA represents a generic acid, acids always have an H in the front, and you react it with water, what it's going to do is this H transfers over to the water. It doesn't just float around as H plus. And so that means you get this thing H3O plus. H3O plus is called hydronium ion. So basically, acid-base chemistry boils down to studying hydronium ion and hydroxide ion. Those are the two main things. Now, hydronium is kind of a long word, and, well, you know, chemists like abbreviations. So a lot of the time, we will say that hydronium equals hydrogen ion, because all it is transferring a hydrogen ion to water. So we can think of the term hydrogen and hydronium as interchangeable for our purposes. And now another interesting facet of the Bronsted Lowry definition that we're going to discuss is that you can't have an acid without a base being with it, because the definition is that acids are proton donors. That means you got to have somewhere to put it. They don't just float around all by themselves, like Arrhenius said. And finally, our last definition is by our friend Lewis, he of the dot structures. So Lewis dot structures, of course, we use to show electrons. So Lewis's definition of acids and bases is all about the electrons, all right? So in this definition, acids are electron pair acceptors. Okay, so our definition of Bronsted Lowry is that acids are proton donors, but here the electron pairs are being accepted. So the donor and acceptor relationship is kind of reversed from definition 2. It's not actually reversed, though. The concept is the same. If you're giving away a proton, so if you're a proton donor, that makes you an acid, according to Bronsted and Lowry. Protons are positively charged. That means you're leaving behind some electrons. So whether you're thinking about electrons being accepted or protons being donated, they're really just two sides of the same coin. They're not actually opposites. Okay, and so then if the acid, the Lewis acid, is an electron pair acceptor, that means that the Lewis base must be an electron pair donor. All right. Now, the beauty of the Lewis definition is that it allows things that don't even have hydrogen to be acids, and that actually agrees with our observations. So on this slide, we talked about characteristics like the fact that acids are sour and that they turn litmus paper from blue to red. They have low pHs. There's lots of things that don't have hydrogen in them that are tart, and they do turn litmus paper red, and all things like this. For example, the compound iron 3 chloride is a great example of this. It has a very low pH. I imagine if you drank it, it would be very tart. I'm not going to do that, but if you did drink it, it would probably be sort of, you know, like lemon juice or something in that family, right? But this doesn't actually have any hydrogens in it, and yet when it mixes with water, it forms an acidic solution. Okay, so Lewis's definition is the most inclusive, meaning it includes a lot of species that don't fit into the other two boxes. Everything that fits into the Arrhenius definition also fits in Bronsted Lowry, so that means definition 2 is the second broadest, and definition 1 is the least broad. Okay, so let's investigate these a little bit. If I have acetic acid, which is this substance right here, when I put it in water, it's going to ionize or dissociate. Those two terms kind of can be used interchangeably. They both mean that the initial compound separates into pieces, and typically it means they separate into charge pieces. So if I kicked off an H+, now this is the Arrhenius definition, so we have to make H+ in order to be considered an acid, then it will produce another ion. All the rest of the acetic acid is still there. So this one, this conjugate here, is called acetate. And this is listed on the back of your periodic table as one of the polyatomic groups. Okay, so sodium hydroxide dissociates also it ionizes, right? So you start with NaOH solid, but when I put it in water, it forms Na plus and OH minus. So it's very similar to what we've seen before. There's a difference, though. Here we have an arrow that points both directions, and on the bottom one we have an arrow that points only in one direction. This is significant. The one that points in two directions actually means that the parent compound and all of the other products here all exist at the same time in the solution. They're kind of switching back and forth. A reminder that we called that equilibrium. Okay, so that's an equilibrium. We'll explore that much more significantly in the next chapter, but it's an important concept because it does apply to acids and bases. Okay, so the Bronsted Lowry definition requires that your acid have another substance present. It's not just by itself producing H+. So instead, for example, if we have HCl, the H is going to get donated, because that's what Bronsted Lowry define as acid and base. And since this is called hydrochloric acid, I know that that's probably the donator. And when it does, it has to have somewhere to send that hydrogen. So it's going to put it onto the water and make H3O+. Also leaves behind the chlorine. Okay, so Bronsted Lowry definition requires a pair of compounds in the products and a pair of compounds in the reactants, because you can't have any donation happening if there's nowhere to put the electron or nowhere to put the hydrogen. So looking at the acetic acid example, what actually happens, as far as we can tell, remember these are particles, so it's very hard to image them, but what we've observed is that the hydrogen doesn't actually hang out as H+. What it does is it looks for a nearby water molecule, and it forms this H3O+ compound. We do have images that do contain H3O+, so we suspect that is the more likely scenario that's really happening. H+ isn't stable by itself, so it seems like it would get gobbled up by water pretty quickly anyway. But at any rate, the Bronsted Lowry definition means that you have an acid and a base in every situation because they depend on each other. Now, this leads to the idea of conjugate pairs. A conjugate pair is what happens when, say for HCl, if you give up the hydrogen to the water, so we've given up the hydrogen and given it to water, what you're left with is the chloride ion, so that makes these a pair. And so since HCl is donating the hydrogen, I know that makes it an acid. The water here is the base because it accepted the hydrogen. Now to figure out which one on the right side is an acid or a base, what I can do is imagine if I went backwards, which one would donate the hydrogen. Okay, and if I can answer that question, that tells me which one is the acid. Chloride has no hydrogen to give up, so that must mean that H3O+ is going to be the acid. Well, if that's true, then Cl- has to be a base. So to assign the conjugate pairs, what we do is after identifying acid and base for each side, we connect them. The acid on the reactant side matches the base on the product side. And you can think of it like the differences from the acid to get to the conjugate base. You just lose a hydrogen. Or from the base, the H2O, to get to its conjugate acid, all you've done is gained a hydrogen. Okay? It's important to be able to identify conjugates, so you might want to practice that with different acids and bases. Okay, so the Lewis definition is a little bit different because it doesn't actually require that the substance have hydrogen attached to it. For example, on the left here we have iron 3+, which is just a single atom, no hydrogen attached to it. And then we have cyanide, C triple bonded to an N. Now, the cyanide has lots of electrons. It's negatively charged, and the iron is missing 3 electrons, so it's, very positively charged. And so what's going to happen is if I have a whole bunch of cyanide around, the carbon is going to be like this negatively charged molecule is going to want to hang out next to the iron because they're, opposites. So the electrons on the cyanide are donated to the iron. So that makes the cyanide the donator, and iron 3 plus the acceptor. So that means that iron 3 plus is a Lewis acid because it's an electron pair acceptor. Okay. Similarly, another example here is BF3. There's no hydrogens in it. It does have a vacant place on the Lewis structure. And then you have ammonia over here, NH3, and it has an extra pair of electrons. So it's pretty logical that the ammonia is going to donate those electrons to BF3, and BF3 is going to accept them. So if it accepts the electrons, that makes it an acid. And if it donates them, it makes the base. There aren't conjugate pairs for this one, so it's just the Bronsted Lowry definition that has conjugates.